At this stage of the game, we've probably worked through a number of polynomial long and synthetic division problems. I wanted to take some time to look at a particular case where we have a polynomial here, degree 4, quartic, and we want to divide it by this binomial. And what's different about this is it's not a big problem if I'm using long division. This binomial happens to have a leading coefficient that is not 1. But in order to use synthetic division, your divisor has to both be a binomial and the leading coefficient of x needs to be 1. So the question that this video is intended to answer is, can I still use synthetic division? Is there something I can do to get this into the right format? And the answer is yes. Before we do that, why don't we try to solve this problem first using long division and see how that goes. So with the long division algorithm, I just write the 3x plus 1 as the divisor, and I'll line up my dividend as 3x to the 4th minus 5x to the 3rd plus x squared plus 7x. And you'll notice that these are in descending order, these powers, or these degrees. And I might as well have a constant term of 0 so that I have a placeholder there, so that when I divide, I get alignment of my terms. And this algorithm is pretty familiar by now. Let me use a different color. I can divide 3x into 3x to the 4th, and that will be found a total of x to the 3rd times. So because I'm dividing this binomial into this binomial, I put this value here in the dividend. 3x times 3x to the 3rd is going to give me 3x to the 4th plus x to the 3rd, and we're going to subtract this entire quantity. These terms cancel out just as I intended. Negative 5 minus 1 is going to give me negative 6x to the 3rd, and I bring down the next term, which is just x squared. How many 3x's will I find inside of this monomial? And the answer to that is negative 2x squared. And now I multiply this monomial times this divisor, and I get negative 6x to the 3rd minus 2x squared. Again, I'm subtracting this entire quantity. These terms cancel out. You have a 1 minus a negative 2, or in effect 1 plus 2, which gives me 3x squared. And I bring down the following term. And I'm getting close to that finish line. How many 3x's can I find in 3x squared? The answer is just x. When I multiply, I get 3x squared plus x. And when I go to subtract, these terms cancel out. 7 minus 1 is 6x, and bring down the 0. Can I find 3x inside of 6x? The answer is yes, twice. And you get 6x plus 2. There should be a remainder of negative 2. And so when I divided, I ended up with a quotient of x to the 3rd minus 2x squared plus x plus 2 with a remainder of negative 2 over the divisor 3x plus 1. See if I can just kind of box that in there. So here we are dividing using long division, and I'm not worried about the format of the divisor, but I am worried about that format if I'm attempting to use synthetic division. So with synthetic division, I want to force this to be a leading coefficient of 1. I can take this entire divisor and this entire dividend, and I can divide them all out by 3, because 3 divided by 3 will give me 1. The problem is it's going to introduce lots of fractions, which is hideous, but nonetheless mathematically feasible. So just imagine I'm dividing this entire polynomial and this polynomial by 3, and the outcome to that would be x to the 4th minus 5/3 x to the 3rd plus 1/3 x squared plus 7/3 x divided now by x plus 1/3. So scary as this looks and hideous and unattractive as it looks, this is now a binomial with a leading coefficient of 1, which is what I wanted. So I can now use synthetic division. And what will that look like? Well, you have negative 1/3 up top. We're going to grab all these coefficients. So 1, negative 5/3, 1/3, 7/3 in that placeholder of 0, and we begin to implement our algorithm. Drop down this value here. Negative 1/3 times 1 is negative 1/3. And now you get negative 6/3, which is actually negative 2. The product here ends up being a positive 2/3. 1/3 and 2/3 is 3/3, better known as the number 1. 7/3 minus 1/3 is 6/3, which is another 2. And now we get negative 2/3 here. So you seem to have this remainder. Now remember, we divided everyone by 3 at the outset. So if I want to make sense of this answer, one way to do it is to say, all right, well, this is my quotient, right? I've got a 1, a negative 2, a 1, and a 2. So we expect that the quotient is x to the third. Remember, we depressed this polynomial, so we went from a 4th degree down to a 3rd degree. We've got x to the third minus 2x squared plus x plus 2, just like we did over here, same quotient. But this negative 2/3 doesn't seem to match up with this negative 2 because we divided by 3 at the outset. So in order to get this to be more recognizable, we need to take this negative 2/3 and we need to multiply it by 3. And when we do, the 3's cancel out, leaving me with negative 2 over what? Not over this negative 1/3, but over the original divisor, which was not x plus 1/3, but rather 3x plus 1. So it is possible to use synthetic division in order to divide by binomials, even when the leading coefficient is not 1. Just to kind of put this in perspective, if you want to, there's a kind of a messier version, which is to take this negative 2/3 and divide it by x plus 1/3 and simplify this. But you'll find that at the end of the day, you're just going to end up with this remainder here. So to save yourself some heartache, whatever you divided by at the outset, just multiply the remainder by that same value and use the original divisor as your denominator.